I'm Brian Lanahan, the founder and chair of the Quantum Strategy Institute, and I am privileged today to be moderating this webinar. We're going to explore how Microsoft's enhanced qubit virtualization system with atom computing's neutral atom hardware has led to jointly generating logical qubits and optimizing the system to enable reliable quantum computation. For the decision makers in our audience, you're going to learn from our speakers their plans that they intend to offer and the opportunities for you in terms of quantum computation. But first, a little bit of administration. Should you have any questions, please use the question and answer box. We will have representatives from Microsoft and Atom Computing to respond to those questions. I'll also be taking some audience questions during the webinar and posing them to our speakers. And of course, I'll be asking questions throughout the session. Finally, what I'd like to do is thank the Quantum Insider, one of the world's leading information platforms, for organizing this session. Now to introduce our speakers. Dr. Krista Svori is the Technical Fellow and VP of Advanced Quantum Development at Microsoft. Welcome, Krista.
Thanks, Brian. It's great to be here.
We also have Dr. Ben Bloom, who is the CEO and founder of Atom Computing. Welcome, Ben.
Thank you, Brian. It's nice to be here as well.
Thank you. Ben, well, let's start with you. What led to the partnership between Microsoft and Atom Computing?
Yeah, I think there's been an amazing wave of advances in neutral atoms. So I started the company in 2018, and since then, Atom Computing has been kind of a leader in neutral atoms, I would say. We were the first to a long coherence neutral atom system, first to mid-circuit measurement, first to 1,000 atoms, to continuous loading, and now with Microsoft first to show a really high fidelity 2-qubit gate and the use of that 2-qubit gate in lots and lots of different logical qubits. But even before that, when we started, it was all about the amazing work going on in the academic community and at Atom Computing, pushing neutral atoms forward. And there was just a humongous set of advances that all kind of came together at once that started making neutral atoms a really viable platform for quantum error correction. And that's about the time that Krista and her team started contacting us.
Fantastic. You know, if anybody in our audience is thinking about gaining more information about the backgrounds of Atom Computing or what Ben Bloom and his team are doing, or Krista and her team are doing, make sure you check out all the YouTube videos that they have available. There's a long history of getting to this point, which we're very excited to be at. Krista, from your perspective, Microsoft has many partnerships, has many activities going on. What was your perspective in terms of generating this partnership with Atom Computing?
Yeah, thanks, Brian. So I think first and foremost, when we look at Microsoft, right, as a company, we really are a platform company, and we're interested to bring the best computational capabilities forward, for our customers, for people, scientists, right, all around the world. So we want to have the best capabilities we can offer, to enterprises, organizations, and people. And so when we think about that and we look at the pace of progress in quantum computing over the last few years, right, one thing we did at Microsoft is really look across the landscape at where do the best possibilities sit in terms of lighting up more reliable quantum computation, right? Where can we get and how do we achieve better quantum computing capabilities? And so naturally, as Ben mentioned, right, in recent years, we've just seen this amazing rapid acceleration, rapid progress in the space of neutral atoms. And at the same time, in the world of quantum error correction and quantum information theory, right, there's also been this wonderful kind of bloom of new ideas, new ways to create better qubits, right? These are really virtual qubits that come together, that orchestrate across physical qubits. And by creating these virtual, we sometimes call them logical qubits in the field, right? By creating these logical qubits, you can get better performance for better computation with the quantum computers. And so it was really, how we came to work with atom computing was really looking at the convergence, right, of this rapid acceleration of neutral atom technologies for quantum computing, rapid acceleration of work in quantum error correction, and what we call our Microsoft qubit virtualization system, right, bringing that to life. And it becomes this wonderful pairing, right, this wonderful pairing from which we can build together, co-build, co-design the world's most powerful quantum machine. And that's what we're working together to do and to deliver in the next calendar year.
Excellent. So when I think about the audience that we have here today, it's a very diverse audience, whether they're IT leaders or business leaders, business professionals, and they're looking for what everybody else is looking for, that commercialized product. But we're using some terms here today that not everybody's necessarily familiar with. Ben, I'm just going to ask you just to help us a little bit between the difference between a physical qubit and a logical qubit, just so people get a sense of why that's important, because we've reached a milestone here within this project that we want to talk about a little bit later.
Yeah, of course. I mean, I think one of the biggest differences between quantum computing and classical computing in general is that pretty much no matter what we're going to do, um, classical bits are perfect. They have, an unimaginably low error rate, whereas physical qubits are generically going to be imperfect. Like there's no physical system that is going to be able to create a incredibly low error rate like in a classical bit. And the question of how you actually try to bridge that gap from physical qubits to something like a logical qubit, where all of a sudden the error rates get closer and closer and closer as you build more and more complicated systems to these classical bits, it's all about actually taking a physical system, for us it's neutral atoms, and actually create the correlations and create the commutations with those physical bits that can be used to represent a logical qubit, a qubit that is now distributed over many of these physical bits. And that's actually what we're doing most with Microsoft, is figuring out how to actually lay out the Microsoft quantum error correction onto the atom computing platform. There's a lot of flexibility in what you can do with neutral atoms. That's one of the exciting reasons why I think Microsoft is working with us. But with all that flexibility comes almost an infinite number of choices you can make. And so you really have to actually co-design the system where you're actually working directly with the folks who are making, amazing advances in quantum error correction to make sure that the platform, the physical platform, can efficiently implement that quantum error correction code. And I think that's where we're kind of doing the most amount of code development.
We heard at a recent conference in September where you started talking about terms like the most powerful machine and the ability to entangle 24 logical qubits. Krista, what does that most powerful mean? And, can you share a little bit more about what this achievement means, not only to your team, but to the industry?
Yeah, so when we think about, why are we building a quantum computer? I think when we think about the most powerful quantum machine, the most powerful quantum computer, we have to remember why we are building a quantum computer, right? First and foremost, we're building it to compute. And to be able to compute things, we cannot compute with all of the classical computers working together in the entire world, right? So we want to build a machine that can compute something, and not just something useful, something practical, something that moves our society forward in a big way. We want to compute those things on the quantum computer. So when we talk about a most powerful quantum machine, What we want to be able to do is perform more powerful quantum computation with that machine, more powerful computation, period, right? More powerful computation than what we can do classically. It won't replace everything we can do classically by any means. These are machines that work hand in hand with our classical computers, with AI models, with Azure, with the cloud compute, right? High performance computing. So when we talk about the most powerful quantum machine and what we're building together there, it is also about integrating it in with the other compute capabilities, right? AI and high performance computing. Now, I think, getting back to logical qubits, right? We talk a lot about this term logical qubits, and then how do we tie that to most powerful quantum machine, right? How do these two things relate? Ben mentioned, right? It's so different in the quantum world, right? In a quantum computer, because things are just so noisy. What does that mean in practice? It means that you are limited in terms of how much computation you can do and still get a reliable result. So with physical qubits, right, with quantum hardware where you're working directly on the qubits in the system, right, those systems can do maybe 1,000, maybe 10,000 operations before a failure occurs. But when we talk about performing computation that we can't do classically, we have to get upwards of 1 million, then 1 billion, then 1 trillion, quadrillion, quintillion operations. We have to go much, much further. Orders of magnitude more computation needs to be able to be done reliably compared to what physical qubits can do on their own. This is the whole point of creating what we call logical qubits. Because what we do is we orchestrate across physical qubits to get these logical qubits, and these logical qubits promise more computation that can be done reliably, right? So it can get us up and over performing 1 million, 1 billion, 1 trillion, and more operations in the quantum computer. So that's the key. So when we talk about building this world's most powerful quantum machine, it's all about getting to reliable logical qubits that then in turn enable more computation than we can get from operating on physical qubits directly. And then driving that amount of computation up to the point where we can show something for science, first, that we can't solve classically, right? That we can drive a solution, get a solution from this machine that we can't get with a classical computer or any amount of classical computing. So that is the idea of the world's most powerful quantum machine, right? The ability to perform operations reliably and enough of them, enough computation that we show something for scientific cases first that we can't do with classical computers alone.
When we think about the industry writ large, there has been a long period of time where people have been waiting for that sort of commercial quantum computer, that suite of products that commercial entities, that academic entities can use. And what you're offering here today has that word commercial in it. But let's take a look at maybe the package which you've described, what you're calling the Discovery Suite. So maybe, Krista, you could start there. You could tell us a little bit about what is the Discovery Suite.
Yeah, so as we just talked about, right, this most powerful quantum machine that we're building together across Microsoft and Atom Computing, it doesn't operate in isolation, right? Quantum computers are not standalone machines. It's very different, right? They integrate the type of applications we want to solve, the problems we want to solve. Even operating the machine itself, right, requires integration with other capabilities. And those other capabilities are high performance compute, for example, high performance compute in the cloud, Azure compute, and then also AI, right? So not only have we seen acceleration of neutral atom capabilities and error correction, but of course there's also been this amazing burst of AI capabilities. And so we want to bring that together with quantum computing and with high performance computing. So this Discovery Suite brings all of that together, right? It's a platform and a suite of tools, of capabilities, right? Everything from a co-pilot to help you in your solution journey, right? A bunch of different capabilities in science, right? Different capabilities in computational chemistry and material science, right? AI models, right? And then all of this is integrated with the quantum machine. So when we say Discovery Suite, it's really about opening up capabilities for new discovery, right? Getting new solutions from the machine, understanding more about the machine, everything from, the researcher, the scientist, someone in an enterprise can work to use the machine, understand, what is it good at, what's novel here, develop new applications, right? We do identify that chemistry and material science really is very, very well paired to quantum computing. Quantum computers are quantum mechanical by nature. And it turns out in chemistry and material science, you really need to understand the electrons, what they're doing, right? You need to understand, it at the quantum mechanical level. So what better than to use a machine that is quantum mechanical to help solve quantum mechanical problems? And these problems are very, very expensive classically, right? They are intractable classically in many cases, and our approximate classical techniques don't work well to get really high accuracy. So this Discovery Suite also is very much grounded in discovery in science, right? Chemistry, materials science, because that's also where the quantum computer can excel. So it's really a suite of tools for discovering new solutions, discovering and understanding the quantum computer and its behavior itself, but also really thinking about driving new solutions in chemistry and material science.
Ben, I'm sure you've been part of these conversations and enjoyed those conversations. What has this meant for your client interactions talking about the Discovery Suite, particularly with a Microsoft connection?
Yeah, I mean, I think it really strongly adheres to what our mission is at Atom Computing. Generally speaking, what we see is that classical computers have given tools to people who don't need to know anything about semiconductor engineering. There are architects, there are mechanical engineers, there's electrical engineers, there's PCB designers. What they go and do is they use a computer to perform simulation, and they try out new products, and they build in simulation thousands upon thousands upon thousands of iterations of these things. And what we want to do with a quantum computer is create that same capability for a new set of engineers, for materials engineers, for chemical engineers. So I think this fits perfectly in with our entire mission at Atom Computing, which is build a quantum computer that is a tool for these engineers to create, the next step forward in modern engineering, which is now engineering materials, engineering drugs, engineering all the things you actually want to do, where you really need to understand the actual quantum mechanical properties of a material. And I think this is the kind of exciting piece that Microsoft is bringing to the table, is not just actually using the quantum computer, but kind of bringing it into this Discovery Suite where you have access to all of these capabilities.
I can see the excitement from both of you. I, as an industry observer, have been waiting for things like this for years, and I'm as equally excited. One of the things that people I talk to, certainly on the user side, is this question of reliability. So how can we, Krista, sort of say that, this is moving in that direction, offering that kind of capability? Can you tell me a little bit about that?
In terms of reliability, yeah, what's really key in terms of the reliability of the machine, again, is going back to these, creating the best and most logical qubits we can that in turn enable, the best and most operations we can. And that leads then to the ability to do complex computations that we can't do classically. And so when we think about driving towards a reliable quantum computer, right, we can't just show that it's reliable for storing information. It's not enough. It's not enough to just detect and correct the errors in the system. That's a must do, right? That's foundational. We have to be able to, understand what and where the noise is occurring so that we can correct for it. But we have to do that while we're computing, right? The whole intention is to compute with the quantum computer. And so we need to drive towards computation. And I think that's one of the, unique pieces, unique unique capabilities that we are fully focused on and driving towards is enabling that reliable computation, right? And it starts with reliable qubits, right? Logical qubits that perform better than the physical qubits themselves, and then showing that you can compute longer and longer, more and more operations with those logical qubits. And that's what we've done together, right? With Atom Computing and Microsoft, we released some technical results on what we call the archive in November. And what we shared is that we can not only create logical qubits using the Microsoft Qubit virtualization system, paired and deeply paired and co-designed with the Atom Computing machinery. We can not only create logical qubits, but we can entangle them, which is a core operation needed in quantum computation. And we can go further, right? We created 28 logical qubits that we then were able to run an algorithm on, right? A full computation. And we can show that that computation performs better using the logical qubits, right? Using these more reliable virtual qubits than operating on the physical qubits alone. And so this is really the type of progress we want to see and drive. We want to drive towards bigger computation, bigger in terms of numbers of logical qubits. That represents what the input to your computation, the input size needs to grow, but then also the size of the compute has to grow in terms of numbers of operations. And so that's what we're doing. We're creating more logical qubits and better logical qubits to enable deep, complex computation that ultimately, when we have around 100 logical qubits, we'll be able to show that we can compute something for science that we can't compute with a classical computer alone.
Ben, you've often talked about how you see this evolving over time and the changing number of qubits and the potential. Can you tell us a little bit about that from a roadmap perspective? Not necessarily, dates, but what does that sort of steps in the roadmap look like?
Yeah, I mean, for us, it's all about increasing the physical number of qubits by a factor of 10 every time we build a new machine. So when we built our first prototype machine, we could get 100 atoms. This new prototype, these new systems we have now, we can create more than 1,000 atoms, about 1,200 or so. And next time we have to go and we have to make 10,000 qubits. We know this because at the end of the day, we need a lot of qubits. And this is not necessarily even just about, neutral atoms. This is, generally across the entire industry, we're going to need hundreds of thousands to millions of qubits, of physical qubits to create all of these logical qubits that Krista and her team are demanding every day. So I think that there's a lot that has to be done. One of the exciting things about neutral atoms, as maybe folks who are on the call who know have already seen, is that neutral atoms have a really, I don't want to say easy, but a very clear path to scalability. Already in academia, people have shown off systems with 6,000 plus individual neutral atoms. As a grad student, used to go and trap tens of thousands or hundreds of thousands of neutral atoms inside optical lattices. It's a very complicated system to bring that individual control, but it's being done at Atom Computing, it's being done elsewhere. And there's a lot that has to go into it, but it's that clear roadmap of really demand that we're going to increase the qubit number by a factor of 10 every time. That's going to make it so we actually get in a reasonable amount of time to hundreds of thousands and millions of atoms or millions of qubits.
So exciting potential and progress here, along with what's already been created. But, Krista, that's not happening on an island. What makes the Microsoft Atom partnership different in our industry?
Yeah, I think, it's definitely not an island. The whole point is to bring this capability to the world so that we can really work to solve some of the world's most challenging problems, right? The intention here is to help solve problems across, across life sciences, chemistry, material science, and beyond, right? It's not limited to that class of problems. And so the point is to bring this capability to the world so that we can also identify other potential solutions here, right? These problems, the problems that one can solve with the machine, right? As people have access to it, understand it, can can program it and do that in concert with AI and high performance computing, right? Integrate it into their existing workflows where things may be very hard, intractable, or not considered, right? Can a quantum computer help solve that part of the problem is a great question. So really the intention is to bring this to the world. It should not happen on an island, and it definitely should not be on an island where the quantum computer exists in isolation, right? It really does need to be with high performance compute and AI. And so part of what we're doing here, right, between Atom Computing and Microsoft, we do have an offering, right? It's an offering. We are selling, selling a machine that's co-designed for this computational capability, and has the ability to scale up, as Ben just outlined, right? Ben and his team are just amazing, right, at continuing to scale the machine to enable, every atom represents a physical qubit. And so in that ability to have upwards of 1,000 physical qubits in this generation we're building now, and then in the next generation to have 10,000, right? This unlocks the ability to go from, around 50 logical qubits out to 100. And that 100 is a very important point, right? When you have 100 logical qubits performing very well, as I mentioned earlier, that's where you start to see new science in terms of new scientific solutions that we can't access classically coming from the machine. I think the other part, in terms of your island analogy here, right? The other piece is a quantum computer need not just produce the solution. I like to think of it also as producing data, right? We can also take the solution from the quantum computer and think of it as data, right? This is data that we cannot produce with a classical machine. So new and different data, but not only that, data coming from a quantum computer, especially, for example, in chemistry and materials science, is going to be much more accurate for certain problems than what you can get classically. And that's why we want it, right? We can get high accuracy solutions. Now, that data can come in the form of high accuracy data that we feed to a classical AI model. Right. So not only do we operate it in concert with AI, we actually can take the data from the quantum machine, feed it to a classical AI model. So augment, say, an existing AI model that's already been trained on a large amount of classical data. We can augment that data set, continue the training with more accurate data coming from the quantum machine. And this can now enable a faster, more accurate AI model. That's a classical model, right? It's deployable in today's infrastructure, in today's machines. So now we can use that model to help predict. And so I think that's a very, very promising avenue for a quantum computer, and it opens up the possibility that we may have very advantageous solutions sooner coming from quantum computers than previously thought.
Fantastic. I'd love to stay with that because artificial intelligence has become so prevalent in terms of its many uses. But can you tell me about the connection with Azure Quantum and where that platform comes into the solution and how important it is?
Yeah, so then as we look at these solutions, right, we've talked a lot about the need for integrated capabilities, right? The workflows here are integrated, hybrid, right? You have integration across the cloud compute in Azure, AI models, and the quantum machine. And so we've built the Azure Quantum platform for this reason, right? Its purpose is to enable this integrated workflow, but then also to enable easy development of applications for, of those subroutines that run on the quantum machine, right? Of applications and algorithms for the quantum machine. So it offers everything, from developer tools, as I mentioned earlier, co-pilots to aid in your development, along with the integration with the other capabilities, which includes advanced AI models, advanced high performance compute simulations, for example, for chemistry. We have accelerated DFT, other generative AI capabilities, right? All of this comes together. And so the Azure Quantum Platform enables this. Now, it also, of course, the Azure Quantum Compute Platform has within it the Microsoft Qubit virtualization system that enables, right, lighting up these logical qubits from the physical ones. And so this whole kind of ecosystem of capabilities comes together and is what we're doing right here with Atom Computing and Microsoft, right, to make it easy to build these solutions, test new ideas, develop new ideas, but also integrate it with AI and high performance compute.
So the business teams that I talk to and the government organizations I talk to are looking for these kind of easily digestible interoperability sort of capabilities in a hybrid sort of environment. And it's not just science that we're looking to solve problems are with, what about that sort of business government segmentation for these potential opportunities?
Yeah, I mean, I think the Discovery Suite really is a great answer to that question because I think right now, the way we interact with Krista's team or the way we want to interact with some of our first customers and partners, it's really about them using a quantum computer to do quantum computing research. And I don't necessarily know if business folks or government folks really want a quantum computer to do quantum computing research. They want a quantum computer or they want the results of a quantum computer to solve a problem. And that's really where the Discovery Suite, I think, is excelling, is that it's really taking the approach of what are the problems they want to solve and bringing that problem solving to the forefront of the actual user interface, such that the quantum computer is there, the quantum computer is helping answer the question, but at the same time now you have this co-pilot for discovery, and you're really getting through from the start to the finish the actual problem you want to solve and not getting buried in just the quantum circuits that are running on the machine or anything like that. So I do think that in some ways this is kind of a perfect marriage where you're actually taking, you know, neutral atom hardware, which is now in the lead, I would argue, for many different hardware platforms, using the results of that, but making sure those results are being put to good use, really trying to solve the problem that someone in a government position or some business is really trying to solve.
So So, Krista, the end user community has been looking forward to a quantum computer of some kind. We've heard about the NISQ era, noisy intermediate scale quantum. It feels like we're progressing past that as we gain these more logical qubits. What are your customers asking for in terms of applications as it relates to, your Discovery Suite?
Yeah, when we look at the applications, as I already mentioned, right, chemistry, material science, life sciences, these are all core application areas. At first it sounds maybe niche to say chemistry and material science. The average person may not be thinking about that on a daily basis, but it turns out 96% of manufactured goods rely on chemistry and material science. That impacts every single human on this planet. So when you think about the materials around you, chemicals around you, food, right? All sorts of things are interacting with something that required understanding of chemistry or materials. And so this is in fact a very large application area, right? A very large space of potential applications that range everything from how we think about paints and colors of paints that aren't toxic, right? All the way over to how we think about producing fertilizer, right? These all rely on chemistry. And so that suite or kind of whole range of applications is large and a great target for quantum machines. Now, of course, one can go beyond that, right? There are folks around the world researching applications, for example, in finance and optimization, right, in other areas as well, right? We're building a quantum computer to enable that exploration, right? Not only to enable the exploration in chemistry and material science, which of course we ourselves are very much investigating and have shown the potential there. But we also want to enable people around the world to explore the applications that they need solutions for, right? So it's not limited to chemistry and material science. Like in that sense, this is a general purpose quantum computer, and it integrates with high performance compute and AI. And so, there's a wider range of applications that one can look at as well.
So, Ben, we hear sort of conflicting messages about quantum and AI and whether they really truly work together. Is it simply faster, more accurate, more options, just like we sort of talked about? What are you talking about with your clients and your community about whether quantum and AI do, in fact, have the opportunity to fit together?
I think they do, and I think it was outlined a little bit by Krista. I mean, I think that, what's really clear from using quantum computers is that they're really big compute, small data machines. And there's lots and lots of things, as we just went over, that kind of fall into that category of big compute problems. And unfortunately, AI, let's be honest, it's a big data, small compute kind of problem. And what we're seeing though is that maybe a quantum computer can actually access something that a classical computer cannot, which is that data, which is that calculation that is fundamentally impossible, due to, correlations among electrons or things like that, that is just not possible to write down the exact wave function for some, material or something like that. And here you have an opportunity where you actually have a system that might finally be able to provide that data for you to go and train an AI on, or go and understand, even just inferences about what should be done in a problem. And so I would say that that is the biggest marriage between quantum and AI. Now, of course, AI can help quantum. I think there's lots of examples of, now in academia and now in organizations too, where they're using AI to make quantum better. And that's certainly something we're interested in and trying to implement ourselves. But I don't know if that's exactly, how we build a quantum computer versus what really matters to our customers, which is how they're going to use it. For them, I think it's going to be about, you know, AI that somehow understands when to use a quantum computer, or AI that has, data coming from a quantum computer. I think these are the two areas where customers are going to see the marriage of these two technologies.
So, Krista, when we think about what Ben just talked about, we get these questions a lot. How can businesses actually get started and maybe even design a strategy around quantum applications that are real, practical, near term? How can they start thinking about those things?
Yes. So there's a number of ways to get started, right? One, of course, we are offering a commercial machine, and this machine is co-designed to enable logical qubits and computation. It will have upwards of 1,000 physical qubits in it, and then of course it comes with this comprehensive discovery suite that we've talked about. So, one way to get started is to quite literally have this in your hands, and get started within your organization or institute, right? And to start to grow, a user base that has an understanding of what this is, how it works, right? Where does it best operate? What kinds of solutions can it give that classical computers cannot? And so I think, beyond that, though, not everyone will be buying a quantum computer. So when we look beyond that, right, what we've worked to develop, at Microsoft is a set of samples of capabilities, right, to start to understand where quantum computers can work. So even in advance of having a quantum computer itself, say in the loop or in the pipeline, we do offer quantum computers in the cloud and Azure. But going beyond that, we also offer tools for understanding and developing applications, right? And then understanding what scale quantum computer will you need for those applications. We call this the Azure Quantum Resource Estimator. We have a co-pilot that can help you write quantum programs and quantum code. And so all of this is available on Azure Quantum, right? So there's ways to access quantum computers today to start to understand. Right now, of course, these are quantum computers that still are operating on physical qubits. So, the intention here with atom computing is to go beyond that capability and enable, more complex, deeper computation. But I think, really organizations need to understand the application space, understand how quantum computers work. How would you integrate it into your workflow, right? So we've also demonstrated integrated end-to-end workflows that, again, bring together the high performance compute, the quantum computer with logical qubits and AI, right? That workflow is a great example. It's a sample workflow of the workflows every application is going to really be using here in the near term. So starting to understand that workflow, ensuring that your systems, are modular so that you can take advantage of such a workflow, right? Learning to integrate it into that workflows is really important. But lots of samples, different tools, learnings, right? Another great way is to start to learn what do quantum computers do? What are they, right? We have lots of tutorials and webinars available as well on Azure Quantum.
So, what's great about all that, we did a survey of registrants for the webinar, and we asked them some questions. For example, what are some of the primary challenges that you've got? Certainly technical expertise was high on the list, and the things that you've talked about allow them to gain that sort of technical expertise in a comfortable way. Secondly, they talked about the lack of use clarity. So, that's why I was posing these questions today about what are some of the applications and why can people start to think about in their own business. They also talked a little bit about readiness, and that of the respondents, only 6% said that they were actually considering themselves as a leading company. About 38% of them said that they were simply experimenting, which is probably not unusual at this stage. Um, you know, from an impact perspective, it was right across the board. They felt it was going to be, minimal impact today to a lot of impact. And that's probably not surprising given the maturity level of various different businesses as it relates to this technology. So, Ben, any surprises there as you think about, the outreach to clients, whether it comes from a clarity perspective or technical expertise?
Well, I mean, I think it goes back to that quantum computers are fundamentally going to offer us different capabilities for compute than we've ever had before. And I think if you look at what's happened with AI, um, there's a huge number of companies that exist now that did not exist 2.5 years ago. And the same thing is going to happen with quantum. The same thing is going to happen with use cases on quantum. And so I think there's a general question there of, you know, are you seeding business opportunities to this new wave of companies, or are you actually bringing that in-house and being a leader in that effort? And I think that is going to be, the tale of quantum computing isn't just about the technical advancements. It's going to be about the proliferation of uses of quantum computers and all the ways that businesses find to actually not exploit that, but to utilize that to address their, the fundamental problems they have to solve for their business.
So we have about 5 minutes left in our session today. It has been a fantastic discussion. Krista, I'm going to ask you the question about what people are thinking about, the threat, the cryptography aspect of quantum. So, how should we be thinking about that, whether in frame of reference of the Discovery Suite or just simply quantum in general?
Yeah, when we think about quantum computers, right, we've really focused on the application set here, right? We're building a quantum computer to help solve, problems that face humanity and society, save our planet, feed our planet, right? We really want to build applications that, benefit our world. Now, at the same time, what we haven't discussed is quantum computers are in fact also good at some other solutions. But here's the good news, right? When they're good at these other solutions, what I mean is, they have the ability to, break the mainstay of e-commerce today, right? The underlying crypto systems, we call it RSA, right? Every time you put your credit card on the internet, it's encrypted. These techniques of encryption can be broken with a quantum computer of the right size. Now, so I think the first thing to realize is that quantum computer is not yet, right? Quantum computers are not yet of the size that can do that. But, we are scaling up. And so we need to be ready. And this is why there's been a whole series of studies and deepening the understanding of how do we move away from that. We want to move to systems, crypto systems that aren't able to be broken with quantum computers. And that's exactly what's happening right now. And if you're in your business, your industry, if you're not yet migrating to what we call post-quantum cryptography, right, and building in that agility in all of your security and encryption capabilities, right, that is what needs to be done first and foremost. So the good news, right, the silver lining is there are classical techniques that are robust to the threat of quantum computers there. So we do want to continue to build quantum computers for the good, right, for the good applications. And we can move very rapidly, right? We need to migrate businesses. Microsoft can help. We have a number of initiatives and programs where we can help ensure the security, of your work. And of course, at Microsoft, it is first and foremost, we have a quantum safe program, a secure futures initiative, right, that really ensures everything we do is safe to any quantum computer threat. But so, really the key for all industries, businesses is to adopt PQC, post-quantum cryptography, as quickly as possible. That's really critical.
So, I guess the message is no longer trying to predict when, but rather getting ready now. Starting to think about what your business is doing, whether you need various different layers and so on. So we're just about at our time. Ben, do you have any sort of parting thoughts that you would like to share with our audience as we, wrap up this session, particularly for such an incredible milestone where you're already thinking about next year and the year after?
Yeah, I mean, I think it's really a question here about, like you just said, almost when, not if. Quantum systems are getting larger and larger every day, and there's advances every day. And I think that we're on a track that's quite exciting. And I would say that there's new amazing error correction work we're excited to work with Krista and her team on. At the very tail end of this, we brought up RSA, and I think if we go back earlier in the webinar, I said the words, big compute, small data problems. And maybe most people heard that and thought, I don't know what that really means. We just had a great example of that. One RSA key, and it's a big compute problem. I think there's lots of examples of big compute, small data problems. And as we start to dig into with more and more useful quantum computers, I think more of those problems are going to surface.
Krista, I've been following your work for years at Microsoft. It must feel like you're, reached a certain milestone, certainly not just within your career, but in Microsoft writ large. What would you have any sort of departing comments for our webinar attendees?
Yeah, I think it's, it really is an amazing, amazing period. It's been an amazing year working with Ben and his team at Atom Computing. I can't say that enough, right? I think it's really been a year of taking theory to practice. We could say theory to product, right? We are building, co-designing a machine, and we have already lit up 28 logical qubits that are computing. And I think this is just the pace of progress here it's so rapid. I don't think there's been a period in my career where I've seen this speed of progress, right? 1 year ago, we did not have logical qubits in the entire industry that outperform physical qubits. We now have, with Atom Computing and Microsoft working together, we have enabled 28 logical qubits that are performing computations. We still have a lot of work to do, which is why Ben and I love our jobs, right? We love what we do. We get to push this to the next level, but I really look forward to when we are all on a webinar again 1 year from now and talking about the kind of compute we're going to be doing at that point in time.
So I certainly want to thank both of you for an incredible conversation. We've talked about powerful machines. We've talked about hybrid environments. We've talked about your partnership. We've talked about applications. We've talked about logical qubits and what the advantages are. And so, when the Quantum Insider gave us the opportunity to get together and talk about these brand new capabilities, hopefully our audience has had the opportunity to think about what does it mean for them? Where can they, sort of inject quantum capabilities in their company? Certainly, Krista has talked about a lot of different resources that are available through Microsoft in various different ways. At the end of this webinar, we'll make sure that you have opportunity to have links to various different resources, whether through Atom Computing or through Microsoft or through the Quantum Insider, so that you have an opportunity to take this to the next level within your organization. Once again, I'd like to thank both Ben and Krista. Thank you so much for your time. Thank the Quantum Insider. Take care.
Okay.